Good morning, folks. This is Todd Coburn of Cal Poly Pomona with Lecture 10 of Aero 3261. Today we're going to be continuing our study into bending, and we're going to focus today on multiple materials. Last time what we covered, we'll cover any homogeneous section that's the same throughout. This will handle sections that are made of multiple materials. For example, if we have say an aircraft stringer or frame that's made of all aluminum, and then later we're upgrading the aircraft for a higher gross weight, we end up having to beef up certain parts. We do that by adding angles and straps and things like that, fastening those onto the structure. Those can be aluminum of a different type or the same type. It can be titanium if we need more strength and stiffness, or they can be steel, each of which would require the methods that we're going to cover today. Let's see how this works. Now, often this is called composite bending, bending of composite sections, because the sections are made of a composite of multiple materials. Nowadays, that word composite, we usually think of fiber reinforced graphite epoxy or similar kinds of composites. But actually, any section made of multiple materials is a type of composite. So when we say bending of composite sections, what we mean not necessarily fiber reinforced. It could include that. It means any section made of multiple materials. So last time we started off by I bent a beam before your very eyes, and we're going to start at the same place. We bend this beam, we see our radius of curvature, we see that neutral surface, and we see our strain distribution as the thing bends, right? We found that the strain was can be written this way. We took a closer look at the radius of curvature, wrote this trigonometric relationship, wrote some different ways of expressing stress and strain and moment and force and moment of inertia, and combined these until we got to a point like this right here. This equation here, this relation for the moment, had E in it. And since each element within our cross section had the exact same modulus, we were able to cancel E with another E term. And that led us to our equation MC over I. Now, if we have multiple materials but they all have the same stiffness, then what we learned last time will still suffice. But if our different materials within the cross section have a different modulus, or if we have the same material with a different modulus, for example, if we load our sample with a moment that causes the part of this section to go into the plastic range of the stress strain curve, if the stresses increase above the yield, that doesn't mean the entire cross section is above the yield. It means only part of it is. So if we have an axial load, then if we exceed the yield, everything is exceeding the yield. We still have the same modulus across the entire section, even though it's changed from what it was. If we have bending, then the extreme fibers where the stress is highest will tend to deform, and that means the modulus will change as we go up the stress strain curve above FTY. And that makes it behave like it's a section made of multiple materials. In fact, that is the foundation of what we will study next semester in Aero 3271 when I teach you folks about plastic bending of sections. So we wrote our equation this way, and then we were able to cancel that E term. Now remember, our I was the summation of the AY squareds. We're going to actually follow the same thing, and what we did, we were able to cancel that by plugging in our stress. See, our stress relation had E, and the moment relation had E, and so those two E's canceled. That led us to these two equations, okay? Now, these were our assumptions for that, and now what we're going to do is look at if our E is not constant. If our E is not constant throughout the section, typically meaning we have different materials, and sometimes meaning we have gone into the inelastic range, then we're going to follow that same derivation until we get to this equation here. And then we can't just cancel out the E. So what we're going to do, if we remember that our I was the sum of the AY squareds, we could say, let's take an I. That I was our stiffness. It was the relative stiffness. And since the E was the same everywhere, that's all we needed. Now, if we have different materials with different E's, then the I is not sufficient to determine how much resistance that section has. It's going to be a combination. To get the relative resistance of the section, we're going to need a combination of the I and the E. So all we need to do is, instead of I being the sum of the AY squareds, we can define a new term, I sub E, which is the summation of the EAY squareds. So we're going to take the area of each little strip, the Y bar of that little strip squared, and multiply by the E of that little strip, and then sum up those values for all the materials. We can call this the moment of inertia, or we can call it the moment of inertia. I like to call it the moment of inertia because it's not the moment of inertia, it's the moment of inertia. It's E times the moment of inertia. Okay? Now we're going to need this term, and we're going to see how we can use this idea to get accurate stresses. So if we defined our moment of inertia in this manner, then our equation can be written like this. And then, recalling from before our stress relation, we can then plug that in and simplify, which allows us to write it in this form. Now, recall here, now notice here that we have the moment of inertia and the modulus in this equation. What this means is our stresses are going to be the my over the moment of inertia times the modulus of whatever little strip. Now this actually is just a baby step forward, and it's rather simple to implement once you understand it. What it means is we're going to be using our equation like normal, mc over I, but instead of I, we're going to use that moment of inertia in the denominator. Then what we're going to do, after computing all of those, we're going to need to look at wherever we want the stress, we're going to need to look at the moment of we're going to need to look at the modulus of elasticity of that point and multiply our my over the moment of inertia by the modulus of the point where we want the stress. That will give us the correct stress at that point. Some texts will calculate the my over moment of inertia and then later multiply by that E. I like to do it all in the same step, and I'll show you how that works. So, however, okay, so we said that we're going to write our stresses like this, my over the moment of inertia times E. The problem is, E is a huge number, and when we multiply huge numbers by small numbers, we tend to get errors creeping into our analysis. So we're actually not going to use, now that I've got you convinced that this is a great idea, we're not going to use the moment of inertia in our calculations. Instead, what we will do is normalize the moment of inertia. So we're going to go and look at our section. We're going to look at the modulus of each little elemental strip, and then we're going to normalize them to one of those moduli. I believe the easiest way, and the one that reduces error the most, is if you take the smallest moment of inertia, if you take the smallest modulus of elasticity, the smallest one for anywhere in your section, call that your reference modulus, and then divide the modulus of each and every strip by that modulus. That means any strip that has the same modulus as your reference modulus will have a n of 1. Any that has a greater one will have an n that's larger than 1. Now you could do this the other way too, but I find it easier to deal with numbers that are larger than 1. They tend to be whole numbers or fractions that are more readily handled, decimals that are more readily handled. If you take the larger one as your reference, you're going to find a lot of really small decimals being applied, and that's going to introduce additional errors. So we're going to define this new variable n. N is just the ratio of the E of each and every strip against the reference E. Now with that said, we then can write the moment of inertia. So we found before we're using the moment of inertia for most of our stuff. If we have multiple materials, we could use the moment of inertia, but what we're actually going to use is the moment of inertia. And what we're going to do is define that is just the sum of the n of each strip times the a of each strip times the y squared of each strip, and sum that up for the whole section. That's our moment of inertia. So we've got the moment of inertia, which is what we use for all standard analysis. We have the moment of inertia, which is one tool that we could use, but we're not gonna. And we have the moment of inertia, which is what we're gonna use. Now, one word of caution. I've never heard anybody ever talk about the moment of inertia or the moment of inertia. This is a Coburnism that I have developed because I think it makes it easier to remember this stuff. Now, others are using the same approach. Some of them do a better job than explaining it than others. Some do a worser job than others. But this idea of defining the moment of inertia is extremely powerful, straightforward, and simple for you to be able to apply practical analysis that's correct. Now, once we've defined this moment of inertia, we then can continue on to write our stresses as the my over the moment of inertia times the n of each and every strip, or of, the n of whichever strip we want to stress. So we're going to take the total moment on the section. We're going to look at our section. We're going to say, where do we want the stresses? Each and every stress will have the moment divided by the moment of inertia of the entire section. And then you'll say, where do we want the stress? If we want it at point A, you're going to take the y coordinate of point A, you're going to put that in, and then you're going to look at what material do you want the stress in at that point. What's the material at that point? And you're going to use the n for that, and that will give you the correct stress. Got it? Okay. With this approach, our area will no longer be the area, at least the area that we use. The moment of inertia is no longer the moment of inertia. However, we're going to be needing what I'm calling the area and the moment of inertia, or the moment of inertia. Actually, I use both terms. The moment of inertia and the moment of inertia. Either one is fine. We're going to need both of those in order to calculate accurate stresses. We'll see how that works in some examples as we move forward. So here's how we can write this generally. Okay, so we're going to use the same approach with axial stresses. If we have a cross section with multiple materials, then the area will be the area of each times its n. Sum them all up, that's the area of the section. If we want the stress associated with that, we're going to need to take the force divided by the area. We're going to need the moment divided by the moment of inertia. And we're going to need our y bar minus I times the n. Both these terms now, because the a is not a but a sub n, and the I is not I but I sub n, both of these terms will need an n multiplied against it in order to get the units right and get the stresses correct. If we had a stress and a moment in another direction, we would just add another term with the other moment and the other moment of inertia and the x's and the n of that section again. Okay, that's our basic approach. Let's take a look at some examples. Oh, we're also going to get a couple special cases in this analysis. So if we have, this is another way of describing it out of Hibbler's text. And what he's doing is we really have two approaches. If we have two materials, a blue and a brown material, and the one material is less stiff. Let's say the blue material is less stiff and the brown material is more stiff. Excuse me, the blue material is more stiff and the brown material is less stiff. We've got two approaches. We can make either one our reference. Option one, if we transform our material to the less stiff material, what we end up doing is it's effectively widening the other material. And in the other one, if we make it our reference equal to the stiffer material, then we'll be effectively narrowing the other material. This is the way most books describe this, and it works but it's actually less, while it's analogous to what I'm teaching you, it's less clear than what I'm teaching you. Here's a little example. Here's how we're going to solve it. This is just like the example, the method that we applied for sections of the same homogeneous sections. We're going to idealize our section just like before. We're going to place our coordinate system on the thing and idealize numbering our little elements. We're going to compute our section properties. We're going to start in the same way. We're going to put our width and our height of each and our y bar of each. We're then going to add, now all you really need is the n here, but I like to put the e for each element. That makes it easier to keep track of to me. Put the e in the table and then calculate the n. Once you've chosen your reference, I recommend choosing the smallest e as your reference. In this particular example, I chose the larger one, and because of that, I have this 0.333 as the n for the second material. If I had chosen the less stiff material as my reference, then I would have had 1 and 3 as my two n's. Those are easier to deal with and introduce less error into the calculations that follow. You see how that works? Anyway, for this example, I chose the other one. We now have n. We then continue on our merry way, but we're going to tweak it slightly. We're now going to put, instead of the area, we're going to put the inertia, which means we're going to take the n of each times the b times the h of each. That's this next column. We're then going to take the inertia times the y bar. That's just multiplying the inertia by the y bar of the section. We're going to sum each, and we're going to use those, as we did before, the summation of the inertia y bars divided by the summation of the inertias to calculate our y bar of the section. Also, you'll notice that the inertia of the section is just summing that first column there. Or actually, it's the 1, 2, 3, 4, 5, 6, 7th column, okay? We then can go on, now that we've calculated our y bar, to calculate the inertia times the y minus y bar squareds and the 1/12 BH cubes. Now, we have to be careful. When we calculate our 1/12 BH cubes, we're taking the n times the 1/12 BH cubed of each and every element. Then we sum up that column. We sum up these last two columns and add those together in order to get our total moment of inertia of the section. You'll notice now we have the inertia of the section, we have the moment of inertia of the section, and we have the y bar of the section. That's the real y bar. If you had not factored your areas with that inertia, with that n term, then you would have the wrong y bar. Okay? Now that we have these values, we can take our loading, determine the moment, and just calculate our stresses by plugging into our equation. Okay? And look at our stress at each place. If we have axial load, then we'll have this first term, P over the inertia times n plus m times y bar minus y over the inertia times the n of whatever point you want that at. So the y and the n corresponds with the individual point that you're looking for the stress at. Does that make sense? And in this case, that gives us these values. Okay? Here's a little example that shows this implemented. If we have a little piece like this with 3 materials, we populate our table and calculate our stresses. You'll notice in my little table, I've got an F sub n and an F. This F sub n is actually a fictitious stress that is before we apply the n. I actually don't recommend doing that. Just plug in your n, plug into this upper equation, and calculate the correct stresses, which are shown over here to the right. This is how Beer and Johnson solves this problem. It uses the Pansy approach that it provides. And this approach works, but like I'm saying, it will work if you're following somebody else's work. It will tend to fail if you try to apply it to a new problem. If you follow my tabular approach, you will probably be able to solve, let me soften that, you have the opportunity to be able to solve a countless practical aircraft problems with more chance of getting it correct. Here's another little example. Couple parts, couple materials. Obviously we got wood and steel, 2 different materials. This is using our tabular approach for getting the stresses. Okay. This is Hibbler's method of solving that, where it transforms one and solves it by hand. Once again, this works, but it will probably fail you if you use this rather than what I give you. Now, if we have a complicated section like this one here, if you try to use what most textbooks give you, you will probably fall short. If you use our method from my class, you will find this is actually not that difficult. Let's see, we have the fail-safe chord. That's this little J over here to the right. That's got 16 million. Everything else is 10 million. If we use a smaller e, the E of aluminum is our reference, then anything made of aluminum will have an N of 1. Anything with titanium will have an N of 1.6. Those are nice, easy numbers to use, and then we construct our table. Just like this, we put in the widths and heights, the y-bars of each, the e of each, and then we put in our factors, n, and then we calculate. And this is using old nomenclature where I'm using a prime rather than a sub n. I developed that a sub n and that inertia and moment of inertia idea a couple years later, and I haven't upgraded all of my slides and charts and everything. So when you see this a sub prime and the I prime, that just means it's the inertia and the moment of inertia. So you calculate your y-bar, calculate your I, and plug in your stuff. You can see the f prime is just that fictitious number before we apply the n. That f is the actual stress. And this is just showing over to the right the relative errors due to this being a non-symmetric section that we pretended is symmetric. It looks like this is total nonsense, but actually the numbers are much tighter than this. They're actually effectively about 6% off, and that 6% is even left when you consider other approximations. Folks that are academics that don't understand real practical structures may be a lot more worried about these numbers. We can talk about this further if you want to. But makes sense. Okay. This is effectively only actually about 5 or 7% theoretically off when you go and you look at what the average stress in each cap is. And if you consider that we've neglected a ton of skin in this analysis, you realize that any apparent error is actually overstating what's really going on. Now, a new idea is the idea of concrete beams. Now, concrete beams require a little more challenging approach. If you pull out your handbook, I believe I augmented, let's take a look, what we were going to do here with, I did, look at this. I augmented it quite a bit. Blah, blah, blah. Okay, so first let me pitch this slide. If we have a reinforced concrete beam or any structure like that, what happens is the concrete has such a low tension strength that it tends to crack out at a low stress level. What this means is if it cracks out, it's not effective. But it is still effective in compression. Even if you have low loads during the life of the concrete, it's liable to develop cracks, which means we can't count on it for tension, which means we're only going to account for any steel area for carrying tension. We're going to count for the concrete that's in compression and only the concrete that's in compression. What this means is the neutral axis of this section is unknown. So we're going to need a more detailed approach to calculate this. What we're going to do is we're going to say that, okay, let's take the whole part of this that's in compression and the part that's in tension, and let's just balance those two areas. And if we did that, we develop this nomenclature here, where we have D is the total depth of the section. You'll notice that's from the uppermost surface of the beam of the concrete to the center of the areas of the little steel rods. The area of the steel rod is approximated is the area, the pi r squared of those, of all those rods, times your n of those, right? And so we can find this neutral axis is from the top, h prime from the top, okay? Now the problem is we don't know where that is. We can find out where it is by, first we're going to need this transformation factor. Next we can write a little, we can sum our forces or calculate the first moment of the area as the area bh times h prime over 2, right? minus the N times A steel, D minus H prime, all that's got to be equal to 0. If we simplify that equation, we get this quadratic. We can solve this quadratic to find out what H prime is and then solve the problem. Now this is actually not as hard as it looks, but it is a bit of a hassle. If you look at your handbook, section 6.3, I have added quite a bit of detail on how to calculate where this is. A lot of these textbooks will show the stress distribution in the concrete as a triangular one, as shown in this middlemost picture. Actually, the analysis that they're using isn't using a triangular distribution at all. It would be fine to use a triangular distribution, only slightly makes this slightly more complicated. But usually what they're assuming is the entire concrete is under constant compression, and so your Y bar to that is to the middle, and the area of the steel is under constant tension. That's the way it does it. This is all shown in my handbook. I have the same polynomial, and then I go on and solve that polynomial so that you can calculate the H prime directly if you have a rectangular beam with steel rods, and then it gives you an equation for the I for that directly. So I have enhanced this significantly. I haven't upgraded my slides yet. You're going to want to read section 6.3 of your handbook carefully in order to solve these. That will give you a more, actually students every semester before this have been doing this just with this quadratic as they do across the world in undergraduate programs. However, if you follow the procedure I have outlined between the last semester and this summer semester, you will find that the procedure I lay out is a lot more straightforward. I still can augment it further and make it even clearer, but this is a big step forward from this slide right here. So make sure you study your handbook carefully. This is one of the reasons you probably wanted to invest in a new handbook, because there are new materials in the back and there's some other things that are of significant use. If you don't have that new handbook, you're going to probably want to copy somebody's pages and add them to your textbook for that. Here is this example played out. This is using, this is out of Hibbler, and for this problem it's calculating the inertia, and it's finding where that H prime is, and then it's calculating the moment of inertia, or the moment of inertia for that section, and then going and calculating stresses, which is a combination of our composite section approach and our concrete beam analysis technique. I encourage you to solve this problem using what I laid out in the handbook, and then this will all be clear about how straightforward it is. If I give you a rectangular beam with any number of steel rods, you'll find the same approach will work. Now, stress concentrations, we also have stress concentrations for bending. For axial loads, it was just this equation, and for bending, it's an analogous equation looking like this. All we need to do is find the table like this from your handbook, or one of the other charts from your handbook. I have a number of sections which cover bending. You're going to go and enter the table, calculate your K in the same manner as we had done before. Here's a few of the Rourke solutions for bending. You can study these at your leisure. I expect you to be able to use any of these. You need to watch out for, in some cases, it may give you the nominal stress. Most of the time, it's just going to calculate a K sub T that's just applied to the MC over I kind of stress. Here's another one and another one. Any of these features, what you're watching for is, do we have a feature that looks like our feature, and is our loading correct? Before, if we had axial load, we use those charts, those sets of equations. This is the similar features, but with a moment applied instead. More on the stress concentration factors for bending. In this particular case, you'll notice this moment is not the total moment on the section, but the moment per unit inch, which can be calculated from the equation give here, 6m over t squared. It's just dropping the b. That gives you a moment of inertia per unit inch. It gives you a moment per unit inch, and you can calculate what the actual stress is. Okay, in this lower one, you got to watch out because what it gives us is a different formula for the nominal stress, and you're going to apply your K sub T against that. So whenever you enter one of these tables for equations, you're going to want to make sure you read that, make sure you understand, is this applied to the normal stress, the net stress, the my over I stress, or is it applied to some other nominal stress that it provides? Okay. Here's a couple more examples. You can look through these at your leisure. Here's a couple more example problems. Let's say we have a lump section, just like we had before. We have lump sections, and in this particular case, we have everything is, let's see, E is a steel stringer. Like, let's say they have a repair, they switch it out with a stringer. Let's say there's a size issue. Like, let's say there was corrosion on stringer E, and the loads have gone up, and and they need more capability out of stringer E. So they go to make a larger aluminum section and it won't fit. So they just switch it out with a steel stringer. This is a very common kind of thing. Usually they try titanium before they try steel. So if they switch it out to steel, now that just obliterated everything that we learned before about calculating MC over I stresses, unless we remember how to handle composite sections. This is easily handled as a composite section. All we have to do is construct our table and add the end column. So we first list our areas, we then list our Y bars of each. We then place in the E of each and then calculate the N of each. If we choose the smaller one, you'll notice that our E of the steel is just 3. If we had chosen steel as our reference, we would have had a 0.333 for all the aluminums, which would have caused introduced all kinds of error into our calculations afterwards. This is maintaining the best accuracy we can have in the simplest manner. We then calculate our inertia and our inertia times the Y bar. We use those to calculate our Y bar of the section, and we can calculate our inertia of the total section. We then can go on. Here's a couple questions for you. Is that the area of the section? No, it's the inertia, but that's what we need to calculate stresses. Is that the real Y bar of the section? Yes, that is the correct Y bar of the section. Okay. We then can calculate this column, the inertia times the Y minus Y bar squareds. Great. And then we can use that, since there's none of these, we're ignoring the bending stiffness about their own axis. We now can just sum that column and get the total moment of inertia or moment of inertia. We then can apply this into our equation. The moment on the total question, is that the moment of inertia? No, that's the moment of inertia, right? But it's the one we need. The sum of the IX term, right, that's gone since we neglected bending about the own axis. Now we can calculate our stresses directly in this table by just plugging into our equation the N times the M Y minus Y bar, or Y bar minus Y, over the inertia, over the moment of inertia, and that gives us the stress in each and every point. Don't forget now what we're doing. To calculate the stress in stringer A, we're multiplying that times the N for A. To calculate the stress in stringer B, you're multiplying this quantity times the N for B, and so on. Okay? That's how it works. We then, if we wanted to, we could calculate the force in each stringer. This is commonly needed for stability analysis. Now you can just take the stress in each, multiply back against the area of each, and that will tell you what the force is of each. You're multiplying back against the area. You'll notice here, let's see, you'll notice that we are multiplying to get the force. Now that the stress is correct, to calculate the force, you're multiplying by the area, not the inertia. That's giving you the total force on that piece. So you'll notice the steel piece, 24,000 psi, multiplied by the area, 2, gives 49,000 pounds. It's not times the N, not times the inertia, okay? So when we're calculating our stresses, it's the Y bar minus Y over the inertia, moment of inertia. But when we calculate the force, it's that stress times the actual area, not the area. Okay? You see that? I think I need another warning in this table. That is all I have for you. Enjoy. Study this carefully. Work the problems carefully so you don't mess up. This is key, important stuff. This is not done as often as last lecture will be done, but this will be done a lot in aerospace structures. Enjoy.